today we're going to talk more about variability. We just worked on mean absolute deviation. Mean absolute deviation is going to work well when you have a set of data that is symmetric and has no outliers, but not a lot of data sets have that. So another thing that we're working on today is going to be called standard deviation. So we're going to start at the beginning. A biologist is trying to determine which sugar is more successful in growing a particular eukaryotic cell. She collected the data below. The diameter is in micrometers, and that's what this little μm symbol is, micrometers. Sugar W, and we've got 19 pieces of data with a checksum of 760, and sugar P, we have 19 pieces of data with a checksum of 760. Now, what I did was I used the graphing calculator, and I already have plugged into stat edit both of my lists. So I have list 1, which is sugar W, and list 2, which is sugar P. And I'm going to do stat calc 1 variable statistics, and I'm going to ask it to calculate. You'll notice it says list 1. And I've got that the mean is 40. I mentioned that before. The sum of the data is 760, so that goes with my checksum. That's good. And then if I scroll down, you can see that there are, in fact, 19 points. The minimum 10, the quartile 1, 34, and median 40, quartile 3, 45, and maximum 70. So it's giving us all the data that we need. Now, the one thing that you might notice is that this particular one has some outliers. So that 10, which is your lower extreme, is an outlier, and that 70, which is your upper extreme, is also an outlier. The actual box and whisker plot stops at 32 and goes as high as 49. So your 5-number summary for the box and whisker plot itself might have 32 instead of the 10 and 49 instead of the 70. The second one that's there, which is sugar P, that one, if we do the same process, stat calc 1 variable statistics, but this time we're going to ask it to switch to list 2 and calculate. You can see from the picture that there were no outliers, so we don't have that issue. We can see that we have a mean of 40, a sum of 760, which matches our checksum. We also have 19 pieces of data, and the 5-number summary 10, 25, 40, 55, 70. So the calculator will do all of that for us at this point. Calculate the mean and identify the median of both collections. So the mean for both, the calculator told us, was 40. And median, also 40 on this one, right? 40 was the median value, or the line that's in the box plot. And then the mean was 40 according to the calculator, also the median. The two sets of data are obviously not the same. Which statistic or statistics can be used to differentiate between the two data sets? So one big thing would be the IQR, the interquartile range. When we talked about variability, we talked about having less variability if the box, or the whole box and whisker plot in general, was shorter or tighter. So once we eliminated those two outliers, we had a much smaller IQR for sugar W because it had outliers. So you do not need to calculate the statistic. If the biologist wants to consistently grow large cells, which sugar should she use? So we would probably say sugar W because it was lower variability. Yes, we had 2 outliers, but the other 17 pieces of data very tightly grouped, whereas sugar P, very low consistency. Measuring spread. In problem 10-60, you saw that in addition to knowing the typical value, it is also sometimes important to know something about the spread of the set of data. One way to measure the spread is to calculate the range. What range of cell sizes did each sugar grow? So the first one was 10 to 70, so that was 60 micrometers. And the other one also went from 10 to 70, which was 60 micrometers. So why is this often not useful? It doesn't show if or how many outliers. It really sort of lets them blend in. So if you were a scientist and you didn't want people to know you had outliers, talking about the range would sort of hide them, as opposed to talking about the IQR. Another method for measuring the spread of the average distance to the mean, called the mean absolute deviation. Determine the distance of each value to the mean. Remember to use absolute value because distances are positive, and find the mean distance. So when we did that, previously we had to find out how far each number was from 40, add them up, and divide by the amount of numbers. Sugar W was 7.05 micrometers for the mean absolute deviation, and sugar P was 16.3. Compare the mean absolute deviations. Sugar P clearly has more variability. The mean absolute deviation should not be calculated if the data has outliers or is not symmetric. Why not? Well, that's because the mean can get skewed by the outliers. And that's why this is not a good choice for this set of data. When the data is not symmetrical or has outliers, the IQR can be used to measure the spread more accurately. So if we look back at the original 5-number summary, 45 minus 34, the IQR for sugar W is only 11, and the IQR for sugar P, 55 take away 25, is 30. So sugar W, 11 micrometers, and sugar P, 30 micrometers. So compare the two. Sugar P still has more variability. And just to be clear, that's not a good thing. We want something that's more consistent, that has less variability. So for all intents and purposes, we are going to go with sugar W so far as being the one that is more consistent, or sort of more reliable even. All right, so now let's talk about standard deviation. Standard deviation. In chapter 4, you learned about residuals, the distance that points are from the line of best fit. In the process of determining the least square residual line, you had to square the values of the residuals to make them positive, because distances are usually positive. You learned that statisticians prefer to make numbers positive by squaring them instead of using absolute value. So standard deviation is another measure of how much variability or spread there is in a data set. Standard deviation is the average of all the distances to the mean after the distances have been made positive by squaring. After calculating the average of the squared distances, take the square root so the units come out correctly. So let's talk about that in English. It says, without using your graphing calculator, find the standard deviation of each sugar in problem 10-60. Now, I'm going to show you how to use the graphing calculator to do it as well, but you need to know where that comes from, okay? So first, we know that both of these sets of data had a mean of 40. So what we would do is say, how far away is each number in the list from 40? So the number 10 is 30 away, and in order to make it positive, we're going to square it. The number 32 is 8 away, and in order to make it positive, we're going to square it. 32 is 8 away, and we're going to square it. 6 squared, 6 squared, 4 squared. I think you get the picture. We're going to do that to all of these numbers. And so we're going to get numbers like 900, 64, 64, 36, 36, 16, and we would continue for all 19 numbers. When you get to 40, you're going to use 0 because it is exactly the same as the mean. You're then going to add up this whole list. And in this case, we're going to get 2,240. But because there's 19 pieces of data, we're going to divide it by 19. And we have to get rid of the fact that we squared all of those numbers. So the last thing we're going to do is square root it. And so what you're going to see is something that looks like this. Okay? It's a lot going on there, right? That would take a lot of work. It would also take a lot of time to show it out in the video. But what we have is every number's distance from the mean. We squared it. We added them together. And then that's our 2,240. We divided by 19 because there were 19 numbers in the data set. And last, we took the square root to counter the fact that we squared them in the beginning. So we would say that 10.86 micrometers is the standard deviation. So on average, any given number in the set is on average 10.86 micrometers away from the mean. And the second one, when I did the same process, the mean was 40. Each number, how far away is it from the mean? Square it, add that set of numbers up. That's the 6,766. Divide by 19 because there's 19 numbers in the set. And then we square root to counter the fact that we squared them to make them positive. That one is 18.87 micrometers standard deviation. So we're getting the same results. Sugar P is less reliable, or we can say it has more variability. So I wrote down the two numbers here. And what you'll notice is this little symbol here for standard deviation, it's sigma. So what is the standard deviation? 10.86 for sugar W, and that symbol again is sigma, or the standard deviation for sugar P is 18.87. It has more variability, or we can say it's less reliable. Now, how do we do it on the calculator? You may have already noticed that symbol. When we took the graphing calculator, and I still have that same set of data, and we did stat, calc, one variable statistics, I want to do it to list one and calculate. When you did that, you actually found sigma every single time. You just didn't know what the symbol meant. So the standard deviation, 10.8, you'll notice it's 5.7, which would round to 10.86. If we did it a second time, stat, calc, one variable statistics, and I want to change it to list two, which is second two, and then calculate, I would get that sigma, or standard deviation here, is 18.87, and that is consistent with what I did manually. Your teacher will demonstrate, did that, how to find standard deviation on the calculator, and we got the same results. So we could do the same thing for the 40 holes of golf event. I'm not going to do it just for time, but I'm happy to do it in class if anyone wants to see that done out again. The standard deviation was probably not an appropriate way to report the spread of your team's golfing data. And why is that? You probably had outliers. When you have outliers, standard deviation is still not a great one to use. The IQR is going to be your best if you have outliers. Now, the 4 sets of data that we worked with had outliers, but they were pretty close, except I think for group 4. But something like group 2, where the data was really tight, only had one very slight outlier, that would have been one where standard deviation would have been a good choice.